Hello students, welcome to ninth lecture of electrochemistry. As we discussed in previous lecture, we are going to discuss about molar conductivity in this unit. But as I said in last lecture, we already discussed that point in detail in our competitive lecture. So we are not going to repeat it in detail, but let us discuss it in short and then we will move on. So today's point is variation of conductivity and molar conductivity with concentration. So all the new points will be discussed in detail and already discussed points will be discussed shortly, but I will put link of that video in the description so that you can re-watch that video if required. So let us start our point. Both the conductivity and the molar conductivity changes with the concentration of electrolyte. Conductivity always decreases with the decrease in the concentration, both the weak and strong electrolyte. That means if you decrease the concentration of weak electrolyte or a strong electrolyte, you will notice its conductivity also decreased because of less number of ions present in it. If we add more number of electrolyte, obviously it will increase the number of ions in the solution, and ions conducts electricity in solutions. So this can be explained by the fact that the number of ions per unit volume that carries the current in the solution decreases on the dilution. The conductivity of solution at any given concentration is the conductance of the 1 unit volume of the solution kept between two platinum electrodes with the unit area of cross section at the distance of unit length. This is clear from the equation G is equal to kappa into A upon L. That means kappa is a specific conductivity, A is the area of cross section and L is the length or distance between two electrodes. So if A and L both are in unity, that means let us say area of cross section is 1 centimeter square and the distance between two electrode is 1 centimeter. So A upon L will become A, and in this case G is equal to kappa. Molar conductivity of the solution at the given concentration is the conductance of the volume V of the solution containing 1 mole of electrolyte kept between two electrodes with the area of cross section A and distance of unit length. Therefore, lambda m is equal to kappa into A upon L, it is equal to kappa. Again, same thing, if we are using unity for A and L both are constant values for our cell. Suppose you have a solid cell in which we are filling the liquid and then we are measuring the conductivity. So volume of that cell will be constant. We cannot change. Suppose you have a glass which has 250 ml of volume capacity, it will remain 250. It is not variable. Second thing, distance between two electrodes. So electrodes are solid piece of metals. Obviously in this case we have platinum electrodes and they are placed inside the cell, so they are not movable, so you cannot change their distance. So L and A both are constant value for our cell, and if they are in unity, then lambda m also it is equal to K or kappa. So L is equal to 1 and A is equal to V. For the solid piece of wire, suppose you have a solid wire or a rod, and if you want to measure its resistance or conductivity, then length of that wire is equal to L and area of cross section is equal to A. But what about the liquids or solutions? For solution, distance between electrode is considered as L, length, and volume of the solution is considered as area of cross section. And as we know, conductivity is directly proportional with area of cross section and it is inversely proportional with length. That means for both normal conductivity, if A increases, then conductivity increases. If A increases, then molar conductivity increases. If L increases, G decreases, and again same thing, if L increases, lambda m also decreases. That means these points are similar for both of them. And now question remains for the concentration. What about the change in concentration? Now, as mentioned here, if A is equal to V, that means volume of the electrolyte, and if it is not unity, then what? Then our equation for molar conductivity will be lambda m is equal to kappa into V. That means volume of solution. Now notice here, V increases, that means lambda m also increases. They are in direct proportional relation. That means if one increases, second also increases. Kappa, let us say it is constant, then lambda m is directly proportional with volume V. So in molar conductivity, we can say that if volume increases, it increases the molar conductivity. But what about the normal conductivity G? In that case, if we increase the volume, we are actually decreasing the concentration, because how can we increase the volume? By adding water or adding solvent. If you add the solvent, then volume will increase but concentration decreases. So here contradiction arises. For normal conductivity, if concentration decreases, then conductivity decreases. But in this case, as we can see, volume increment increases the lambda m. That means if volume increases, that means concentration decreases. And if concentration decreases, still molar conductivity is increasing. That means relationship between G and C is they are directly proportional. If volume increases, if concentration increases, then normal conductivity increases. But for lambda m, they are inversely proportional. If concentration increases, then lambda m decreases. If concentration decreases, lambda m or molar conductivity increases. We have a graph for that, as we can see in this graph. Let us discuss about this. So on x-axis we have concentration raised to 1 by 2, and on y-axis we have molar conductivity lambda m. So as we can see, let us talk about the strong electrolyte first. So this black straight line actually represents strong electrolyte like KCl, and this blue line represents the weak electrolyte like CH3COOH. So on x-axis we have concentration values C raised to 1 by 2. So as we can see, as we decrease the value, actual conductivity, molar conductivity is increasing. Okay, as you move from right to left on x-axis, value on y-axis increases. That means it represents as we decrease the concentration, conductivity, molar conductivity of the solution increases. So why this happens? Why with decreasing concentration, conductivity or molar conductivity increases? So we have some few explanation regarding to this, but before that let us discuss some points about this paragraph mentioned here. So in this paragraph it is mentioned as we increase the volume, we are actually adding the solvent inside the solution. So by increasing the volume, we are actually decreasing the concentration. So keep in mind, for finding molar conductivity, you have to maintain 1 mole quantity of the solute inside the solution. That means no matter what is the concentration, but amount of solute must be 1 mole. At that point, conductivity is called molar conductivity. So that means first of all, at the starting point, use 1 mole quantity of solute and then start adding water into it. And at different volume, find the conductivity of that solution. That means we are using the same solution. First, let us assume we need 10 molar solution. So use 1 mole of the substance. Let us say we want to find a conductivity of NaOH. So 1 mole of NaOH is equal to 40 grams. So use 40 gram of NaOH. That means it is 1 mole of NaOH inside the beaker, and then add some water. We need total volume is equal to 100 ml. Suppose this is the solution's level when we make it total 100 ml. So now 100 ml contains 40 gram or 1 mole of NaOH. It represents at this point concentration is equal to 10 molar. Now find the conductivity of this solution. So it is called molar conductivity of the solution because we have 1 mole quantity of our solute. Now if you want to find the conductivity of 1 molar solution, then you have to add some more liquid solvent into it. Suppose total volume is, after the addition of some solvent, is now 1 liter. So now 1 liter contains 1 mole of NaOH. So obviously concentration will be 1 molar. Similarly, if you want 0.1 molar concentration, then add total 9 extra liters of water into it. So total volume will be 10 liters. Now 10 liter contains 1 mole of NaOH. It represents concentration will be 0.1 molar. So same amount of solute is used in each and every concentration, but different volume of the solution is used, so that you will get different concentrations. We have less volume, that means 10 molar concentration. We have higher volume, that means 1 molar concentration, and highest volume we have 0.1 molar concentration at 10 liters. Now notice number of NaOH is kept constant. It is 40 grams or 1 mole. Now as mentioned earlier, conductivity depends on number of ions. So that means maximum possible number of ions will remain same in all of these cases, because we are using only 1 mole of NaOH. So NaOH when splits inside the solution, it will produce NaOH, Na plus and OH minus. Okay, so that means one NaOH molecule produces total 2 ions. That means 1 mole of NaOH can produce maximum 2 moles of ions. This is the maximum limit of 1 molar concentration of this given solution or NaOH. Understand it this way. Suppose we have 3 different concentrations. First, as mentioned earlier, 100 ml containing 1 mole of NaOH, that means 10 molar solution, 1 liter containing 1 mole of NaOH, and 10 liters containing 1 mole of NaOH. So we have 3 possible outcomes. Now in this case, 2 different factors acts against each other. First of all, number of ions. Now if we decrease the concentration, ionization increases. Why it increases? Because as we increase the volume, distance between 2 ions produced during the ionization is increased, and there is less possibility that they will attract each other. Okay, one of the ion is positive, one of the ion is negative. So if they are closer to each other, then there is a possibility they will attract each other and they will form a molecule. But if they are kept aside or they have larger distance between them, then they do not attract each other, and that's why they will be stabilized as an ion inside the solution. So this is the first reason. With increasing volume, distance between ion increases. That's why more and more number of ions will be produced. That means percentage of ionization increases. So in that means in concentrated solution, percentage will be dropped. So let us say in 10 molar concentration, our strong electrolyte gives 80% dissociation. That means out of 1 mole, 0.8 mole will be dissociated. In 1 molar solution, let us say 85% ionization occurs. That means 0.85 moles out of 1 mole added will be dissociated, or it will produce ions. And in 0.1 molar, let us say 90% dissociation occurs. That means out of 1 mole, 0.9 moles will produce ion. So that means number of ions will be maximum in dilute solution, because all of them contains same amount of electrolyte. So this is the first reason. Second reason is, as mentioned earlier, for conductivity, area of cross section is directly proportional. That means if you increase the area of cross section, more number of conductivity or electrons will shift from one side to other side. So it increases the conductivity, and for solution, area of cross section is equal to volume. So if volume increases, it increases the movement of ion. Understand it this way. Suppose you are standing in a room, okay, and we have a door in a room which has a size. In that size only maximum 3 students can pass at a time. Okay, so now let us assume we have total 30 students in a classroom and all of them are leaving the class. So per second, let us say maximum capacity of the door is 3 students per second. So only 3 students can pass because of the width of door. So all the 30 students will pass through the door at 10 seconds. They requires 10 seconds time. Now suppose same class, same student, but comparatively broader door. Now width of door is increased and now total 5 students can pass through it. and we have 30 students, so what will be the time requirement? 6 seconds. So if we increase the size of doors, more number of students at a time can pass through it, and that's why we can do it quickly. Same thing is applicable with volume. Shorter volume will allow comparatively less number of ions to pass through it. Let us say if in this case only 3 ions can pass at a time, then if we increase the size, more number of ions will pass through it, and in this 1 liter highest number of 10 liter volume, highest number of ions will pass from one side to other side. That's why they will feel less resistance against each other, and they will quickly move from one electrode to second electrode, and that's why conductivity increases. Okay, so we have two different factors, ionization and volume of the solution. That's why ionization will be highest in least concentrated solution, and volume will be highest in least concentrated solution. These two factors increases the molar conductivity of our solution. That means diluted solution. Concentrated solution gives less value of molar conductivity, and dilute solution gives highest conductivity. And here conductivity, that means molar conductivity. So as we can see here, for KCl this relation is straight. It directly gives a straight line. With decreasing concentration, conductivity is increasing. But when we reach to the zero, actually practically we cannot reach to the zero, but theoretically we can do it. Now observe this graph. Practically, let us say we got some data. Suppose we carry out 5 different solution, practical on 5 different solution, and we got data for that 5 different solution. For one solution you got a point here, for second solution you got here, for third, for fifth, and for fourth and fifth we got these type of points on this graph. Then we connected all of this graph and we got a straight line, as we can see here. But when we stretch this line further, we can touch it at y-axis, and this value at y-axis when concentration is equal to 0, which is not possible practically, but we are doing it theoretically. At this point, conductivity of this solution is called limiting molar conductivity, and this is the symbol of that limiting molar conductivity. So what limiting molar conductivity says? So we can say that it is the maximum possible value of molar conductivity of that given solution. You cannot get more than this value. This is the maximum limit. At this value, which is not practically possible at this time because of infinite dilution. Zero concentration represents infinite dilution. We have infinite distance between ions. That means no other ions are attracting or repelling each other. So they are completely independent from each other, effect of each other. So they are freely able to move electricity from one side to other side, and 100% ionization occurs. Okay, so 100% ionization, that means whole 1 mole of electrolyte will produce 2 moles of ions if we are using KCl, NaCl or NaOH like electrolytes. So all the 100% molecules will dissociate in ions. So you have maximum number of ions and we have maximum number of volume. At that point, maximum possible value of molar conductivity is called limiting molar conductivity, and practically we can say that you cannot find it, but we are doing it using this graph. We find some points. When we connected this point, you got a straight line. Now stretch this straight line, and the intersection with y-axis is the value of limiting molar conductivity, and it is constant for every electrolyte. So this is the way you can find the limiting molar conductivity of strong electrolyte. But what about the weak electrolyte? As you can see in this case, for weak electrolyte like CH3COOH, we got a curve, and it is not touching the y-axis. That means as we used method in strong electrolyte, simply stretch the line, and intersection with y is limiting molar conductivity of given strong electrolyte. You cannot do it with weak electrolyte because weak electrolyte is not at all connecting with y-axis. It is now parallel. if we carry out more, it will go parallel with y-axis. So they are not going to touch with each other. So how can we find the limiting molar conductivity of weak electrolyte? For that we have to move on our other point and we are going to discuss it. So first of all, what is going on with weak electrolyte in this graph? So initially, as we can see, very minor number of ions will be produced because this is weak electrolyte. Weak electrolyte, that means they will produce very less number of ions inside the solution. So initially, because of very less number of ions, there is not much change in the concentration, but still we can notice concentration is increasing with dilution. After some point, we will notice conductance is drastically increasing, and after certain limit it will take a short and straight up line will be observed. So why this type of straight line observed? Because at after certain point these weak electrolytes will dissociate quickly and they will produce very large number of ions. That means initially their dissociation percentage were low. After certain low concentration, this percentage will drastically increase and it will produce large number of ions, and that's why this type of short in the conductivity is being observed. Now strong electrolytes. For strong electrolyte, lambda m increases slowly with the dilution and can be represented by the equation lambda m is equal to lambda m naught minus AC raised to 1 by 2. It can be seen that if we plot a graph of lambda m against the concentration raised to 1 by 2, we obtain a straight line with intercept equals to lambda m naught. Now because of print mistake, consider this value as lambda m naught and this box actually represents 1 by 2, c raised to 1 by 2, okay, and this symbol is also lambda m. So when we plot the graph of these, you will get a straight line and interception is equal to lambda m naught and the slope is equal to minus a. The value of the constant a for the given solvent and temperature depends on the type of electrolyte, that is the charge on the cation and the anion produced on the dissociation of electrolyte in the solution. So it is a whole other thing, we can do it, but we need some instrumentation and we have to carry out practical to find the value of a, or you can find the value of a from the graph as we observed in previous point. Thus NaCl, CaCl2, MgSO4 are known as 11, 21, 22 electrolytes respectively. Now why they are called like this? They are simply represented by their charge. In NaCl we have Na plus and Cl minus, that's why 1 1. For CaCl2, Ca carries plus 2 charge and Cl carries minus 1 charge, that's why 2 1. And for MgSO4, Mg carries plus 2 charge and SO4 carries minus 2 charge, that's why 2 2 electrolyte respectively. All the electrolyte of the particular type have the same value for A. So here one example is mentioned. Now do it yourself if you find any difficulty, because solution is already mentioned below, so I think no difficulty will be faced by you. But still, if you find the difficulty or if you find anything which is not understanding by you, then feel free to ask. We will discuss this numerical in next lecture. Otherwise we will start our next point, Causal's law.